Hi, this is an update on my alum crystal's growth. So since the last video, my crystal has grown dramatically. Last time it was observed that there was no crystal growth in the solution. However, this week it can be observed that there is a large crystal growth at the bottom of the vial. And this is a very dramatic change from last week. It was also noticed that a significant volume of the water in the vial has evaporated since the last video entry. There are several environmental factors that may be affecting the growth of my crystal, one of which may be that it has been relatively cold outside. Because the temperatures outside have dropped, the heat in my dorm has raised dramatically. Due to the increase in heat, the temperature in my dorm has also increased, and subsequently, my room has become significantly less humid. As a result of the increased heat and decreased humidity, more water from the vial may have evaporated in the time period from the last alum video to now than during the previous weeks. As water evaporates, the volume of water the alum is associated in decreases, and therefore the solubility of the alum in solution also decreases. Because the solubility decreases, the alum precipitates out of the solution in the form of a solid crystal. So using what we know about crystal growth and equilibria, I'm going to answer how we can use a saturated solution of alum to grow one giant high-quality single crystal. So one way that we could do this is through seed crystallization, and another way is through slow evaporation. So let's talk about slow evaporation first. One of the largest factors that affects the growth of a large, high-quality crystal is the temperature at which it is stored at. If there were a choice between growing the crystal at a low temperature, at room temperature, or at a high temperature, the ideal solution would be at room temperature. This is because a clear crystal will form when it forms at a slow rate. When crystals grow slowly, impurities will be prevented. However, if crystals grow at a fast rate, smaller crystals will tend to form. Ultimately, we need to have a slow growth to synthesize a high-quality large crystal, and this will occur at room temperature. This procedure was what was done in our methods and in our experiment, and it resulted in the production of a single high-quality crystal. Another method that was used to produce clear crystals, or could be used to produce clear crystals, is a technique called seed crystallization. To do so, the same procedure that was utilized to produce the original alum solution would be repeated. In this procedure, approximately 5.5 grams of alum would be dissolved in 40 milliliters of water. Ideally, crystals should form at the bottom of the vial within a few days or by the end of the week. All of the crystals will be removed from the vial into a clean container. The crystals with a smooth face and a regular octahedral shape will be chosen to be a seed crystal. The remaining alum crystals will be redissolved in solution by heating the solution to approximately 60 degrees Celsius. The seed crystal will be carefully suspended from a stick into the alum solution through a string. And the top of the container in which the solution is placed in will be covered by a Kim wipe to prevent dust and reduce temperature fluctuations. By using this method, a large high-quality crystal will grow. This procedure was not done in this experiment, as we allowed the crystal to grow at the bottom of the vial rather than on a string. So to explain the scientific significance of despacing, when chemists synthesize a material, they usually want to run an analytical test to determine what the material is, what it looks like, or how it behaves. For crystalline metals, this usually begins with identifying the structural arrangement of the atoms, where the atoms are, and how far apart they are from one another. One of the defining characteristics of a crystal is its periodicity, which is a small atomic scale pattern that repeats itself over and over in every direction. This characteristic profoundly affects how crystalline materials interact with light, and those interactions can be manipulated and measured into giving us the arrangement of the atoms. The repetition in a periodic arrangement of atoms means that we can identify many sets of parallel planes of atoms. There are possible planes in many directions in a crystal, but some planes are more prominent than others. Each set of parallel planes has a consistent distance between neighboring planes. This distance is what we call the d spacing. If we understand the spacing and angles between the planes, we can reconstruct the entire crystal and figure out where all the atoms are. That's the significance of the d spacing. Bragg's law also explains the significance. When X-rays are aimed at a crystal, some waves of light come in together or are in phase, but some may leave the crystal out of phase. If we want the waves to leave in phase with each other, the path length difference must be an integer multiple of the light's wavelength. So using the powder X-ray data for Alum, this is a calculation for the d spacing for the most intense peak in the diffraction pattern. So we can calculate the d spacing by using Bragg's law. Bragg's law comes in the form of n times lambda equals 2 times d times sine theta, as you can see here. So in the diffraction pattern posted on Canvas, we can see that lambda here is 0.15418 nanometers. And we can see that the most intense peak of the diffraction pattern occurs at a value of around 21 degrees, and that's 2 theta. So because we want theta in our Bragg's law equation, we did 21 divided by 2 to get 10.5. And we were given that n equals 1. So when you plug into this equation, you get 1 times 0.15418 times 10 to the negative 9th in meters equals 2 times the d spacing times sine of 10.5. So we calculate d to be 4.23 times 10 to the negative 10th meters, or 0.423 nanometers.